Dear student, hello. I have the pleasure to share with you the presentation of a solution of an exercise about electrostatics and particularly about continuous charge. The exercise is the following. Consider a circular ring of radius r and center O uniformly charged with linear charge density lambda. Find total charge Qt of the ring. Find the expression of electric field E produced by the ring at point M located on the z-axis. Find the expression of potential V at the same point using two methods. Direct calculation, I mean Coulomb's law, and the expression of electric field found in the second question. Assuming that the potential is 0 at infinity, and this last sentence is boundary condition. I will explain it later. Let's go with the first question. But before starting, I would like to speak about continuous charge. Continuous charge is as if we take a discrete charge, grind it, then sprinkle it or distribute it over wire, a surface, or over volume. So depending on the dimensionality of the medium where the charge is distributed in, we can discuss three cases. The linear density, charge density, surface charge density, and volume charge density. Here in our case we have a wire bent to form a circle, so the density of the charge is here linear, obviously, lambda. Even in our picture it seems that it's surface, but it is hollow inside. I mean it's empty, and the distribution is only in the circumference or the in the peripheral side. For total charge, now the idea is to break down the medium into elementary portion dl, and each portion carries elementary charge dq, so that we can write lambda equal dq over dl. And for so dq is equal lambda dl. For total charge, now it's the continuous summation of q of dq, and the continuous summation is integral. Here in our integral, the differential element of integral is dl, so L lies from 0 to 2 pi r, I mean the total circumference or of the circle. Now, since lambda is constant, we can take it out of the integral. Here it is said in the text that the charge is uniformly distributed. Uniformly means each portion dl of the ring is charged with the same amount dq, so lambda is constant. Integral of dl equal L between 0 and 2 pi r, the wholly circumference, and here is the result of q total. Now the second question is about electric field produced on the point M situated on the z-axis. The idea is the same. We break down the ring into small elementary portion dl, and each elementary dl carries elementary charge dq, and each dq produces elementary field dE at the point M. According to Coulomb's law, we can write dE equal k dq over d square, and we add the unit vector. dq is equal to lambda dl. We replace it, and d is the distance between the elementary charge and the point M. Here we need to write d with respect to data to the exercise, I mean z and d. Here you see in the picture it's very obvious that d square is equal z square plus r square. We replace in the expression and we get this one. The next step is to find the total field E. So, as previously said, that here we need to make a continuous summation, which is integral. I would have liked to do integral to find E total, but it's forbidden. Unfortunately, I can do it because the dE produced by each dq of the ring are not in the same direction. I will give you explanation on look at on the picture. Here I choose dq, I choose it randomly, okay. So the dE produced by this dq, look at, is not in the same direction as the dE produced by the first dq. So what we need here, we need the relation of Schall, because the vectorial summation is performed by the relation of Schall. But here also the relation of Schall, we can do it because we have infinity of dE. So we are facing a problem here, but this problem has a solution. Let's go for the solution in the next slide. The solution here is to decompose dE into two components. dE has two components, dE long z-axis and dE x y on the plane x y. Look at the presentation here, dEz, and I show the angle alpha, and the other component dE x y on the plane. I can put it here, is the same, and mathematically we can write dE cosine alpha and dE sine alpha. Now I replace dE with its expression. Now I need to write cosine alpha and sine alpha with respect to data to the exercise. Look at the picture. I show the angle alpha in the other side. They are the same. Alpha is opposite angle at the vertex. Okay, so cos alpha is z over d, sine alpha is r over d. I replace in the expression, I get the final expressions of dEz and dE on the plane. Okay. Now I can perform the integral without any problems because dEz, all the dEz are in the same direction, all the dEx or y the same thing. So we are ready to perform the integral. But before making or before integrating, I want to use a trick in order to make the calculation of integrals easier. The trick is the axial symmetry of the ring. Here you see in our ring, each dq has its symmetric in the other side, okay, because we have the z-axis, which is axis of symmetry, and this charge dq produced an elementary field with, you see, with the component dEz in the same direction and the same magnitude as that produced by its symmetric charge. Thus, due to the symmetry, we double Ez. For the other component, I mean on the plane, you see that it has the same magnitude by opposite direction as that produced by its symmetric charge. Hence, they cancel each other. That's why I can put here equal 0 due to the symmetry. Okay, our differential element now is dl. Okay, and now here L lies from 0 to to pi r this time, not like in the first question, because we have put here 2 due to the symmetry. I mean, here we deal only with the half of the ring, because the other half is expressed by this number 2. Okay, now z, lambda, r, k are constant with respect to L, so we can take them out of the integral. Okay, the integral of dl is equal L between 0 and pr. We replace, and we can put this result with respect to q as function of q. Okay, here is the final expression of EZ. So the total E is entirely held by the z-axis, because the other component is equal 0, and we have the final expression of E, and you see that it depends only on z. Now the expression of potential V at the same point using Coulomb's law. It's very easy here. Why? Because V it's not a vectorial quantity, it's scalar quantity. So dv k dq over d, we replace lambda dl, we replace the expression of d, and here we for V without discussion we use the integral of dv. Okay, and the dl lies from 0 to pi r. Here lambda, z and r and k are constant, we can take them out of integral. Okay, and we have this result, final result. It depends also in z, only on z, in z. Now a calculation of V by using the expression of the electric field. It is the second method. Here the idea is to use an expression lying the potential V to the field E. It's this one. Okay, pay attention here. dl has nothing to do with the circumference of the ring. dl here is the displacement between M to a point M prime. Okay, and if it exists a field between these 2 points, it will exist systematically a difference of potential dV between these 2 points. Okay, we replace the expression of E. The expression of the displacement is 3 dimension, and we get here that product between K and dl. We perform it, we get this. So here it's equal 0 because K and I are perpendicular. The same thing for K and J, and for K and K we have 1. So the result is equal dz. We replace in dv, and we get this. Now V is the integral of dv. Yeah, we have the integral. Look at here now. The dz is our differential element of integral. You see that here z is not constant anymore now. Okay, so we can take it out of the integral. What we can take out of the integral is kq only. Okay, so here we have an integral to perform. So far the physics is finished, so it remains only mathematical work to do, which is integral. Let's go for this integral in the next slide. Sorry. Okay, you have integral mathematical work. You see, when we have the numerator numerator here, you see that it is a derivative of the denominator. Don't worry about this this power. Okay, it's not very important. Okay, when we have this thing, I mean numerator is derivative of the denominator, always you do changing of variable, which is u equals z square plus r square. Now we need dz with respect to du, we derivate and we get this. We replace in our integral and we get integral with respect to u, and it's very easy to do. Okay, the integral is this one. You look at, we add the c because the integral is not bounded. Okay, so we replace and we get this. It's very easy, yeah. Okay, now I replace in v, I get this. Now our problem now is c, the determination of the constant c. This constant c is determined by the boundary condition. V equals 0 for z equal infinity, yeah. It means that here, the more we go far from the ring, the more the influence of the ring will decrease, will increase, decrease, will decrease. So we replace here v equals 0, z by infinity, here 0, and we get c equals 0, and you see is exactly the same result as found in with the other method, the first method, which is Coulomb's law. And thank you for your attention.